So we will get into those. So a couple random questions. I know I haven't gotten to everybody's questions yet. I have not had time to grade all the quizzes yet this week. But I graded some and have some good questions about the periodic table, as well as a question about a psychological condition. I'm not sure if it was we consider psychological, if it's rooted in the physiology, rather than just being purely mental. This is a condition called synesthesia, where people basically get their sensory data mixed up with their auditory processing and words. So basically what happens is people can see colors that correspond to certain words or certain phrases, or they can taste things. So anytime somebody says, "Welcome to chemistry," you hear bells to go along with those words, or you smell cinnamon. And it said it actually happens a lot after brain damage, after a concussion. Not a lot. It happens when it happens. Most frequently, is after some sort of traumatic brain injury. And our best understanding for this at this point is basically all emotion and conscious thought and processing of verbal words is kind of encoded in the same channels that transmit all of our sensory data. And what can happen sometimes is your brain sort of loses the decode things to separate the words from sensory data. And so you wind up with certain words triggering that word's meaning in your mind, but also triggering sensory data in a different part of your brain that's physically in a different location. And our best understanding at this point is when you get a traumatic brain injury, that it can basically scramble the ability to decode and separate those two streams of information, which is kind of a weird thing. It's not a very common condition. There was a good book written about it. I'm trying to remember what it was called. About a kid who got into a car accident and came away with synesthesia. I'll have to think about that. I don't remember what that book was called. But very interesting, and really goes to show we really don't understand that much about how the brain works at this point. We understand we can map out specific parts of the brain that fire and respond to certain stimuli, so we can say that this part of the brain is involved with processing, say, visual input. But we don't necessarily know exactly how that is transformed into, say, the concept of the color red. Is a weird concept. And it's something that's tied to how we experience things. So this is a really interesting question, and the answer is basically, we don't know entirely how it works, but we think it has to do with not being able to separate those visual cues anymore, or just the nerve bundles that actually send that sensory information wind up getting their wires crossed, essentially. So something that should trigger the idea of I hear a bell also triggers the color cyan. So you see specific colors that correspond to these other sensory data, which is weird.
Well, can you also build on that of how in a lot of day-to-day situations we associate certain emotions with color? So in a lot of times if you're hearing something and all of a sudden theater does it all the time, where it'll shift the lights to more of a blue tone.
Yeah.
And immediately start to feel a little bit more sad, or oranges happier and stuff like that.
So some of it is cultural.
Okay.
So growing up in one culture, you learn to associate certain colors with different things. For instance, black with funerals in America, but in other cultures, black is not a color that you would wear to a funeral. Mm-hmm. So there are certain characteristics and some symbolism that is tied to where we grow up. But part of it is also basically, so the way that we evolved to process sensory data started with just being able to intake in information around us. The earliest examples are basically single cells that have these little light-sensitive proteins that basically allow the cell to move towards the light or away from the light. That's all it is. They don't have any other sensory data. But then as organisms get bigger, they started getting more and more the ability to get other sensory data and then sort of put it together with cause and effect. last time I saw the color red, this happened. And it's unconscious because your brain uses the same processing pathways, both for seeing the color and processing the experience in the memory, and also for predicting what's going to come in the future as a result of last time I saw red, this happened. So it's part of it is the fact that we've evolved out of these very, very simple sensory, the sensory data processing into much more complex systems that involve emotions and memory and cause and effect that are all running sort of under the hood of your brain, so to speak. And we don't necessarily have a good way, because all of them use the same processing pathways, we can't necessarily separate out emotion and memory from I see this, which is why smelling something that reminds you of your childhood triggers a flood of memories, right? Might not be in any sort of similar situation to, say, Christmas dinner where, you got smell pecan pie and that takes you back to your childhood. But the fact that you smell it now triggers that mostly because they use the same channels and it's all sort of coded together. And that's kind of what's happening here is basically you're getting these misfires where some of those signals are going where they're not supposed to now. And you're triggering other memories or other colors or other auditory data. But really, a lot of it is we don't understand that much how consciousness in the brain works very well at all. They're very, very much in the early stages of understanding what a neurotransmitter is, let alone how all of these different systems interact with each other. So there's a lot of research to be done in that. It's a field that's blowing up right now. But a lot of questions about psychology and neurotransmitters end with, well, this is kind of what we think now, but who knows? Which is basically where I'm going to end this one. Somebody asked about, this one is somewhat relevant since we've talked about protons, neutrons, and electrons, and how those are the smallest pieces that make up atoms. The smallest thing that we're aware of now are what are called fundamental particles, which, and a quark is a version of that. So this is all fits in what's called the standard model of physics, which makes, let's see, which basically has a list of what the different fundamental particles are, and quarks are some of them. You need to click on it. That's what I want, this. So basically you have quarks, which are these purple ones here. Then you have photons and bosons and gluons and Higgs boson and all these what are called leptons down here. These are all how different fundamental forces work together. But at their most basic, as I understand it, they all have approximately the same, all of these fundamental particles have approximately the same size, the same mass. But you put them together in different ways and they interact in different ways, and that can change how that mass is measured in the physical world. You put together two things that are about the same size mass-wise as an electron, but if you put them together right, you get a proton, which is 2,000 times greater in mass. So theoretical physics and fundamental forces are very, very weird, and a lot of this has actually been established since I was in school, so I didn't learn any of this in school. I only know what I've picked up along the way from this. So physics instructors might be a better person to ask, or even better, be a physics major. And then you get to learn about all this on your own. Maybe add to this. But so to answer your question, quarks at this point, as I understand it, are still the smallest piece of matter of which we're aware. And when you put them together, they interact in really funny ways. For instance, two up quarks and a down quark makes a proton. But two down quarks and an up quark makes a neutron. And if you can switch one of those up quarks to a down quark, you can turn a proton to a neutron, but you give away an electron in the process. Weird stuff starts happening in the nucleus when you start changing things around. And that's also related to making antimatter. Because antimatter is basically the exact same as regular matter, except with the charges flipped. So a proton weighs the same as an antiproton, but an antiproton has a negative charge, and a proton has a positive charge.
So doesn't that just make it an electron?
No, because it still has a mass that's equivalent to a proton. So it's got a mass of 1, but with a negative charge instead of a positive charge. And so there's anti-electrons, which are the size of an electron, but with a positive charge. So antimatter is basically all the same rules for physics apply, just with opposite charges. And antimatter exists naturally in the universe, but the problem is when antimatter touches regular matter, they both disappear. And all of the mass turns into a giant release of very large amounts of energy. So we don't have very much antimatter in our solar system, probably in our galaxy naturally. But other galaxies, in theory, could be made entirely of antimatter. But we can't tell because you can't tell antimatter from matter visually. They look the same, they behave the same. They're going to have the same wavelengths of light emitted, but with opposite charges. So, but we don't use, I don't think we use the large colliders to make antimatter. I don't know how they do it, but they actually managed to make something like almost, I'd say it was close to a gram of antiprotons in Berkeley. And managed to keep them from touching any regular matter for like half a second or something like that. They did it, they used magnetic fields to keep it away from everything else under a very, very intense vacuum. And they were actually able to make a measurable amount of antimatter for half a second before it was destroyed. So we can make antimatter, and there are nuclear reactions that produce anti-electrons naturally. So antimatter is weird, but it really follows the same rules. It's just opposite when it comes to the charges.
When matter and antimatter they both disappear, doesn't that violate the law of conservation of mass?
No. Well, yes, except it's not really the...
Yes, but really no.
Well, you're going to hear that a lot, especially in quantum, but it's not really the conservation of mass. It's the law of conservation of mass and energy. So if mass disappears, you have to make energy according to that equation. However much mass disappears times the speed of light squares gives you that much energy. So mass can be created and destroyed. Mass is really just another form of energy.
Yeah, I guess
it's just a form that has mass. And you can take that mass and turn it into pure energy in the form of light if you happen to have a reaction like that happening. Mark?
Well, if you have like, I don't know, you have like pro-matter and antimatter like separated, wouldn't they just cancel each other out and that would equal 0, I guess? Like,
if you allow them to touch, they have to get close enough to react. And in theory, so one theory says that there should be as much antimatter in the universe as there is matter as a result of the Big Bang. And so, but if it all got brought back together, it would all annihilate once again, and we'd be back to the form of pure light energy. But I don't know if the numbers still work for that one, or if that's just a working hypothesis for some. They call them cosmologists.
Is that like, I guess you can say like it could be. Is that like yin and yang, almost like a kind of an analog? I guess I don't know.
You certainly could say, I don't know Eastern religions well enough to be able to say 100%.
Yeah.
But it definitely is the same but opposite.
Yeah.
It has that similar quality. I don't know that you could give it any other qualities beyond that, because as I recall, like yin favors like 2 elements and yang favors the other 2 when it comes to like water and air versus earth and fire or something like that. I don't know enough about it to say one way or the other though, really.
I have no idea.
It is interesting from a philosophy standpoint too.
I thought yin and yang just represents opposite yet coexisting forces.
I think it depends on what religion you're talking about.
Yeah, because like 3 different religions use the yin and yang.
Right, and we're getting off topic since this is a chemistry class. I try to stay out of religion because I make everybody mad if I get into religion. So let's get into the more relevant quiz questions. Somebody asked about isotopes. Phrased it this way: I'm just having trouble understanding them. Why are they so different? The answer is basically they're not different. 2 different isotopes of the same element are going to have almost identical chemical properties. Literally, the only thing that's different is going to be the mass. But since almost all chemistry is based around charges and electrons and protons, carbon-13, I'm just putting this back up here so I can point to it as we keep going. Talking about the periodic table. So say carbon-13 versus carbon-12, chemically they're going to be identical. Just the mass, carbon-13 is 13 grams per mole, carbon-12 is 12 grams per mole. We can tell the difference based on that. On this one, this sample is almost entirely carbon-13 versus carbon-12, just by looking at grams per mole, but they're going to react with other elements in a way that's pretty much identical. Which is why, for the most part, we only really care about what's the average mass. We don't really worry about using different isotopes that often, unless we're getting into radioactivity. Because different isotopes have different levels of radioactivity based on, if you mix neutrons and protons in different ratios, you wind up with different nuclear reactions happening or at different rates. So unless we're talking about nuclear reactions, we're going to treat all isotopes basically like the same with a different number of neutrons. How do we detect the charge of an ion, and is it possible the ion can have a charge that's not a whole number? Well, if we say that our fundamental unit of charge is an electron or a proton, then no, you can't have a charge that's not a whole number. On it, that its most basic, you have to deal with integer numbers of protons and electrons. Electrons are a fundamental particle on that chart I was showing you. So you can't have half of a fundamental particle. And same with protons. They have to have integer number of charges relative to the number of particles we're talking about. They're all going to be very, very small number of coulombs, like 1.16 times 10 to the minus 19 coulombs, which is a unit of charge. But if we define it in terms of an electron has a charge of 1 and a proton of -1 and a proton has a charge of +1, then it's always going to be integers, whole numbers, I mean. And this question is essentially asking how do we use the periodic table to tell protons, neutrons, and electrons? Well, unless I say a specific isotope, you can't really use the periodic table to tell what isotope we're talking about. Because the periodic table is always the mixture of isotopes that are found in nature on Earth. But as far as number of protons and electrons, just using the atomic number to count your number of protons, and then using the charge to figure out how many electrons you have relative to protons. So formulas, I don't really like to use formulas with this. You can write formulas, but then you have to remember formulas. So I can write that charge equals number of protons minus number of electrons. That'll give you the right overall charge. But then you have to remember this and what everything represents. Personally, I find it easier to just remember the idea that protons are positive, electrons are negative, and count them and add them together so that you get the charge. So we don't really have formulas per se to do this because it's more about just counting and knowing what mass number means versus the charge means and the atomic number. And so I'm going to focus more on how do we use the periodic table to answer these questions instead of giving specific formulas for these. If you really like formulas and you really want to remember this as a formula, come to me and we'll go over some formulas that we could use. So I'll probably just make them up on the spot that will allow you to plug in numbers and get an answer. But I'm going to present it the way I think first, and you guys let me know if that works or doesn't work for you. So, moving on, talking about the periodic table some more. We've been using it a little bit to talk about these different isotopes and different elements. We're going to talk about Mendeleev. So Mendeleev is this, I guess Dumbledore is a good description. He just sort of looks like he's shattered as a person to me. But it could be because I know his life story a little bit. He was the youngest of either 19 or 16. The historical records differ. And he was born to a middle-class family in Russia. And immediately after he was born, his life starts going downhill. His dad was a professor at a university that taught literature, and right when Mendeleev was born, he started going blind. And this is Russia pre-Bolshevik revolution, blah, blah, good speak. And so it's not like there were unions to protect your job. If you lost your eyesight and you couldn't teach literature anymore, you were no longer a literature professor. See you later. So they went from having a very comfortable life to being almost homeless when his mom got a job working at a distant cousin's factory in the same city. And less than 6 months later, the factory burned to the ground. And again, no unions, also no insurance. So they're not rebuilding the factory at that point. So now they were homeless again. They moved across the entire country. Moving across all of Russia that's a long way. It's a big country. Because his mom thought he was special, and like all moms do, and then chased down like, okay, well, I'm going to get him enrolled at this really cool school for kids not kids, I think this was when he was like 12. Basically, like to put him on a college track so he could go to university. And so by this point, like half of his siblings have also died. He's on a totally different continent than where he was born, with no money in a new city. He was also just not a very nice person. Some people are just like, they can make their way by, have all these tragedies happen to them. They're still nice people. That was not Mendeleev. He was just a real jerk by all accounts. I don't know why, but you can speculate. But what he did manage to contribute is that he noticed that if you list elements by size, that a pattern shows up. So prior to this, they had listed elements alphabetically. They had listed elements by all sorts of different properties. They kind of just made all these tables at the back of books. But he noticed that if you put them in order of size, every 8 elements, you get some repetitive patterns. So element 1, hydrogen, has similarities to fluorine, and 8 elements later is chlorine. Fluorine and chlorine have similarities. And then if you do the same thing with the noble gases were 8 elements apart. And so basically what Mendeleev did is he took that information and said, well, I'm going to put everything with similar properties and I'm going to put it into columns. And I'm going to make this square grid of elements where everything in a column reacts similarly to everything else in that column. So effectively what he did was he invented the periodic table. They knew what elements were before that. They knew that certain elements behaved in certain ways and even had them grouped like similar ways sometimes. But it wasn't until Mendeleev that they put it into a form that looked like this. And this is still a simplified version, but this is, they didn't know about all of the elements at this point. And it wasn't nearly this clean because this is all being done by hand or on typewriters. So the earliest ones look something more like this, which is tricky to see what's happening here because we're not used to looking at it. It's also listed, the groups are listed in Italian. So I think that this was an early copy of somebody from Italy's periodic table that they took from Mendeleev's version. So it's gruppo instead of group, or whatever maybe the Russian word is also gruppo, but I think that most of these are in Italian, if I'm remembering where I got this properly. But what he was able to do is he basically said, well, there's this big gap here in my table that I made. There should be something there. And essentially, he was able to predict not just that new elements should exist, but also what properties they have before anybody had ever even detected them. And so some of the ones that are the biggest examples are scandium, gallium, and germanium. So germanium is right there. Scandium is a transition metal. It's over here. And gallium is right next to germanium. So it had some refining to be done. It wasn't perfect. But this is also a good example of just how much of a jerk Mendeleev was, or was perceived to be, at least by the science community at large. So Mendeleev predicted these elements should be there. But then another group from Germany actually discovered germanium before Mendeleev or anybody from Russia or anywhere else. Instead of naming this element after Mendeleev, since he predicted it should be there, the scientific community at large voted worldwide to name it after Germany, which were huge rivals of the Russians pre-World War I. So basically, as a direct screw you to Mendeleev, they said, no. We're naming this after the Germans because you're such an asshole. Was effectively what that was all about. And it took until everybody who had ever met Mendeleev had died before they actually named an element after him. Mendelevium is all the way down here.
Wow.
When he's predicting all these elements should exist way up here in the 30s. It's basically because we had to wait for everybody who had ever met him to die before anybody would agree to naming an element after him. It tells you something about the guy's personality. Clearly a great mind, a great thinker. Also, just as clearly to me, not a pleasant person. And that happens sometimes. All right, so why do we have these repetitive rows? Why do we wind up with these repeating properties that happen every so often? Basically, why doesn't this just keep going? Why is there this repetitive structure?
Energy level.
And it's energy level, right? I left it up on the screen for you.
Thank you.
Because it turns out that these properties, most reactions are not changing the number of protons or neutrons in an element, which means most chemical reactions that are happening because electrons are moving around. So what we're going to see in this class is, unless we're talking about nuclear reactions, anything that's changing is a result of electrons. They wind up being most significant when it comes to predicting properties and predicting how things will react, because they're the only things that can really change. You can't change the nucleus easily. So as a result, we wind up with the electrons, and the way the electrons are arranged winds up being really, really important in chemistry. We get to getting into quantum mechanics. This is a really cool picture. Quantum mechanics is really, really fascinating because it's the first time in history, really, that all of the experts, pretty much worldwide, on a certain area of study were able to physically be in the same place at the same time. Up until about the late 1800s, travel was so hard that if you were researching with somebody in Siberia, you researched by, maybe if it was really important, you wrote them a telegram. But generally, you were writing letters back and forth, or publishing papers, then waiting for somebody else to respond to you 6 months later. So this is one of the first times where you could get all of these experts worldwide into the same physical space at the same time and let them hash things out together. So there's some really, really cool stuff that happened. This is at a conference at a place called Solvay. If you want to know more about the history about it, you can just Google. There's a full Wikipedia page about the Solvay conference. I believe this is the 1927 Solvay conference. And it's colorized. It was black and white initially, but basically all of these bolded names won Nobel Prizes.
I see Einstein up there. Is that?
So that's a little bit hard to see, but all of the red boxes won Nobel Prizes in physics. Green boxes won Nobel Prizes in chemistry. The dotted boxes means they didn't directly win a Nobel Prize, but their students did for work they contributed to. So we had a huge number of the greatest thinkers of the last 300 years in the same place at the same time. And what they would do all day is they would get together and they would all present their research. They would give these seminars, basically. And then at night, they would stay up and drink and argue about what it all meant. And so a lot of Einstein's greatest quotes, greatest hits, come from this. And Niels Bohr, this guy right here, was one of my favorites. He was the one who always had the good comeback for Einstein. You know, there's the famous Einstein quote, "God does not play with dice." And Niels Bohr is the one whose response was, "Einstein, quit telling God what to do." And you notice the only person circled twice is Marie Curie. So this is early enough. She was still alive. She was old. she probably already won one, if not both, of her Nobel Prizes at this point. And interestingly enough, after her husband died, she actually had pretty much a lifelong love affair with this guy, whose name was Lorentz. But they only saw each other a couple times a year when they went to conferences. There's all sorts of, this guy right here is Heisenberg. He always looks like every picture I've ever seen of Heisenberg, he looks like a creeper. He's kind of like hunches over and sticks his head forward. It just doesn't look like a guy that you really...
Not very photogenic.
Yeah, not very photogenic. We'll give him the benefit of the doubt. He's just not photogenic. But he did a lot of work with Pauli, who's right here next to him. And we're going to talk about pretty much all of these circled names in one way or another. And yeah, it's really fascinating. That's Schrodinger right there with the dapper little bow tie. So Schrodinger's cat, if you've heard of Schrodinger's cat, that's that Schrodinger. Who else was on here? Even if you don't know their names, they probably have a name or an equation or a constant named after them. Basically, the only person that's missing is Planck. Max Planck was already dead, I believe, by this point.
Planck's on there.
Is he?
Yeah.
Just like a dude.
His name's down on the bottom.
Oh yeah, you're right, by Curie. I don't know why I don't have him circled, because maybe he died before they gave him a Nobel Prize, because they don't do Nobel Prizes posthumously. So if you happen to do something really, really important, but die before the importance is recognized by the scientific community, you never win a Nobel Prize.
That's BS.
It is. He deserves better than that. It's also possible I just missed dragging a square around his head, and he did win one. All right, so I'm going to preface this. I'm setting you up because I want you to understand this is weird. Things in quantum don't behave the way you expect them to. Niels Bohr said it best. If you're not shocked when you first come across quantum theory, then you probably didn't understand it. Because things just behave differently at quantum levels.
Doesn't gravity just stop mattering?
No, not so much. We don't deal with it as much. We're dealing with such small particles that there are other forces that matter more than gravity when you get to small enough distances. So we're going to talk a little bit about waves. I'm going to give you some background, and then we're going to say how waves and matter are really the same thing, which should seem weird, because it is.
Of what?
Right. So let's talk about it. If you have waves, and the waves are coming up to a barrier that has a gap in it, when you have a wave passing through it, think about waves in an ocean coming up to the entrance to a harbor. Most of the waves will hit the wall and bounce back. Some of the wave makes it through, but the thing is, when you do this, the waves that make it through don't go through as a straight line. They're diffracted when they go through this gap. And you wind up with this curved surface. You start with something with the waves totally flat, and when they go through this barrier, they come out curved on the other side. Which is weird, but okay. Let's say waves behave like that. Take my word for it. Waves behave that way. If you do it with particles, if you just throw things, basically, at a gap, some of them will hit the wall and bounce back, and the ones that go through will keep going in a straight line. So in the 1800s, there was this understanding that particles behave differently than waves. Unless your particles are small enough, and your gap is small enough, in which case the particles start behaving like waves. So you can kind of think of this a little bit if you imagine you have a giant bin of golf balls and a really tiny gap that you're trying to throw golf balls through. Most of the time you're either going to miss and you're going to hit the wall and it bounces back, or it goes through. But some of the time you're going to hit the corner and it's going to bounce off at a funny angle, right? So basically, because the particles, when you get small enough, can interact with the sides of this, you actually wind up with small enough particles behaving like waves and spreading out in a way that looks like this, in a way that doesn't match Newtonian physics. And here's another interesting one. If you have light, or any waves really, if you have a wave source and you have two gaps instead of just one, a wave will come through and you'll have two wave they will act like you have two wave sources now. Same way, it's going to diffract the same way as we were just looking at before. But now if you have two wave sources, these waves can interact with each other. And you wind up with constructive and destructive interference. So constructive interference is when two wave peaks happen at the same time in the same place. You wind up with a wave that's twice as big as normal. And destructive interference is when you have a wave peak and a wave trough hitting each other at the same time and adding up to nothing. They counteract each other. A positive plus a negative winds up adding up to nothing. So at this point, they started to figure out, okay, well, waves behave differently, and light behaves like this too. If you shine light on two slits, the light photons will interact with each other in a way that instead of just getting one band of light here and one band of light here, you get this what's called a diffraction pattern. It's the result of these photons acting as waves and interacting with each other, and essentially canceling each other out in some places. So if we go back here, we did the same thing and said, what would this look like over here? You would have one bright spot in the middle, and then it would sort of fade until it was totally dark, right? So you'd have a bright spot that got kind of progressively darker on either side. It's really hard to shade accurately with a dry erase pen when you're trying to go fast. But you can imagine kind of what it would look like, right? Bright spot that gradually fades. And here, if we were measuring it, we would have either, it would not be any shading. You would have total black, and then white where the particles are hitting, and then total black again. There would be no gradient whatsoever.
Like a laser pointer.
Like a laser pointer, kind of. When we do this two-slit experiment, we don't just get two of these centered around each of the slits. You wind up with this diffraction pattern, where the interference means that you wind up with destructive interference in some places and constructive interference in others, and you get this pattern that looks like this. So that tells us light's a wave, right? That's cool. That's nice to know. It's awesome. Light's a wave. The problem is that under certain circumstances, light also acts like a particle. So this is actually what Einstein won his Nobel Prize for. Is actually not for E equals mc squared. It's for what's called the photoelectric effect. And the photoelectric effect is this thing they've noticed already at this point. They said, okay, if you take a vacuum tube, and you take a metal and another metal, and you apply a big enough voltage, you can get electrons that jump from this metal to that one. So in other words, like those cathode rays that we saw before, and a lot like the plasma that we saw in those tubes in lab today. What Einstein recognized was that if you have, that it was governed entirely by the frequency of light that was being shined on that metal surface. If the frequency of light was too small, it didn't matter how much light you had, how bright that light was. If the frequency was too small, then no electrons were emitted. But as soon as you cross that threshold, they call it threshold frequency, the more light you had meant more electrons. But it didn't matter, once you reach this threshold, it doesn't, increasing the frequency doesn't change how many electrons you get. The only thing that changed how many electrons you got was how intense the light was, how bright the light was, not what color it was. Once you hit a certain point. So essentially what they came to realize, and what Einstein won his Nobel Prize was realizing that this means that light is quantized, meaning it comes in discrete packets, basically a whole number of pieces of light. Effectively, what this is doing is you're effectively throwing baseballs at something, trying to knock off electrons. If you don't throw the baseballs hard enough, it doesn't matter if you hit it or not, you're not going to knock anything off. When you get above that threshold, one baseball can knock off one other thing, can knock off one electron. But one baseball can't knock off 2 electrons. So the only way to get more electrons is to throw more baseballs. So this idea that light itself has a discrete number of objects that make it up, that was what we call photons now, was revolutionary because, but wait a second, light's a wave.
It's both?
It's both. Light comes in these discrete packets called photons, but it also is a wave simultaneously.
One question of how.
So it turns out everything behaves as a wave when you make it small enough. Electrons behave like waves as well because they're small enough.
Okay.
And that's actually what, where is it? I can't remember what the guy's, De Broglie, knew it was Italian. De Broglie, his contribution to this was the idea that all matter has some wave nature to it. But for the most part, if you get above a certain threshold, the mass part takes over and it behaves as either a wave or a particle. But when you get small enough, things behave as both. And I think I have it. No, I lost it. I'll have to find that one and bring it to class on Thursday. The de Broglie wavelength is part of what led to this. But so this is what Einstein's conclusion was that got him the Nobel Prize. Light is actually tiny particles with wave-like properties. And the energy of each photon of light depends only on its frequency. Every photon moves at the same pace. Every photon has the same speed. And so if all photons have the same speed, but some photons have more energy than others, that energy must be contained other ways, right? Because it's not like a baseball, where to give it more energy, you throw it harder, right? This is saying that every photon travels at the exact same speed, therefore any extra energy must be in the form of frequency. A higher frequency, even though it's traveling at the same speed, means that that photon has more energy. Right? And so that's what we used in class, right? Energy of a photon is equal to Planck's constant times the frequency. Has nothing to do with the speed of light, because all photons are going the same speed. If you combine that with the idea that the speed of light is equal to the frequency of light times its wavelength, we can get this equation. This is really just taking this, which is just a function of all waves have this same equation. The speed of the wave times the frequency of the wave, or equals the frequency of the wave times the wavelength. So if you're using C, it's specific to light, but sound waves have this same equation too, and waves in the ocean have the same equation. The only difference is what the speed is. All right, so we can put it together and then get an equation for energy that's based on wavelength. But here's the raw version. It's just energy is equal to a constant times frequency. It winds up telling us that an individual proton has a very, very small amount of energy because h is so small. H is 6.626 times 10 to the minus 34th. So a decimal point and 33 zeros and then a 6. So it's a really tiny amount of energy. But that allows us, we can essentially say, every photon has energy that's only based on frequency. And that's why you had to get above a certain frequency to knock electrons off for that photoelectric experiment. When you were below a certain frequency, your photons didn't have the energy to knock an electron off. Then as soon as you crossed over that frequency, now every baseball that you throw has enough energy. It's just a matter of how many you throw to tell how many electrons you could knock off. But if your light doesn't have enough energy, if it's below that frequency, it doesn't matter how many photons you shine, you're not going to knock any electrons off. So I've already talked a bunch about Einstein, but I'll talk about him a bit more for a second because he published this paper, and he published special relativity, which is E equals mc squared, and he published a paper on Brownian motion, which is about how things move at microscopic scales that's based on temperature. And he published, I can't remember what it does, there's one other really, really important paper he published the same year, all in the same year. Any one of those papers is a career for a normal person. Einstein published 4 of them in 1 year. He and Newton were actually very similar that way. And they had what they call Anno Mirabilis, which in Latin means miracle year. I think it's how it's spelled, something like that, where it's basically, what the hell? Where was this? Newton did it when he invented calculus so that he could study orbits of planets. He did the same thing. I think it was also 4 big papers the same year in 4 distinct areas from each other. Yeah, fascinating when you look at the history of this and how this all worked. Also worth noting, everybody likes to say that Einstein was bad at math. Einstein was not bad at math. Einstein was bored in his math classes. He got bad grades in math, but he was very good at math.
Yeah, didn't he master differential and integral calculus at like 15?
He was teaching himself the same things that Newton invented on his own in his regular math classes, which is why he was getting bad grades on things like arithmetic and long division, because he was doing calculus, multivariable calculus on his own time. Yes, he got bad grades in math, but he was still very, very good at math. Also, one more historical note about Niels Bohr, since I forgot to mention earlier. This guy who had all the quips for Einstein, he was functionally illiterate. He actually could not read. He actually had to dictate his PhD dissertation to his mother, who typed it for him. So not everybody is an Einstein or a Newton, and even if you are that bright, doesn't mean you're well-rounded, doesn't mean you don't have troubles learning. I think probably, last I heard, I think they would have probably diagnosed him as severely dyslexic. But in the late 1800s, nobody knew what that was. They just knew that he couldn't read. So luckily, he was in a position of enough privilege, he was able to keep going to school despite the fact he couldn't read, and was able to come up and be a contemporary of Einstein and all these other amazing thinkers. Just goes to show, it doesn't always matter where you start, or you don't have to be good at everything. Everybody has troubles learning some things. All right, so let's look at frequency and light. This was also groundbreaking in the 1800s when they first discovered the electromagnetic spectrum, because up to this point they had this idea that everything that existed in the universe could be perceived by human senses. So effectively, you might need a microscope to see things that were really small. You might need a telescope to see things that are really far away, but you could still see them. This was the first time it really became clear that there are things in the universe that human senses have no ability to perceive. We see this tiny little sliver of the electromagnetic spectrum. Naturally occurring sources of all of this other type of radiation is totally invisible to humans without the aid of advanced instruments. But it occurs, it's just not the most prominent form of radiation on our planet. Our sun only puts out light in this narrow region for the most part. So our eyes are adapted to only see these colors, these wavelengths of light. If we lived around a different sun, if we evolved around a different sun that had a different wavelengths of light that it emitted, that was a bluer sun or a redder sun, our visible range would be shifted to match whatever the visible range is, what's the most prominent source of photons around that particular sun. But all of this other stuff still exists, and we use it for other stuff now that we know it's there. But radio waves, microwaves, infrared light, ultraviolet light, X-rays, gamma rays, they didn't know any of that was there until they started looking for it, because humans can't perceive any of it. So this idea that the that the energy of a photon is related to its frequency, this opens up a whole new range of things to study too. This is a logarithmic scale in terms of frequency, where every one of these marks is a factor of 10. So visible light has a frequency of about 10 to the 15 hertz, or 10 to the 15 cycles per second. But gamma rays go all the way, they're naturally occurring light that goes all the way up to 10 to the 24th cycles per second. And so in other words, it's, what is that going to be, a billion times higher in energy per photon than 10 to the 15? 10 to the 9th versus 10 to the 15? And radio waves, on the other hand, are down over here. Also worth noting, microwaves are over here. Everybody's always worried about microwaves causing cancer, right? Or cell phones, things like that. They're so low in energy. They're what we call non-ionizing radiation. They are technically radiation, but it's so low in energy, you're never going to be able to knock an electron off of anything. So as a result, you're not going to really be able to cause any sort of cancer if you're dealing with microwaves and radio waves, which is what cell phones are down in the radio wave region. So it's interesting. People always have a tendency to be worried about new technology. You do not need to be worried about cell phones and microwaves when it comes to cancer. You do need to be worried about cell phones when it comes to reprogramming your brain and neurotransmitters and dopamine fixes, because social media is designed to be addicting, but it's not the obvious danger of worrying about the radiation itself. It's what other humans are doing with our knowledge of conditioning. But that's neither here nor there. You guys all have some experience now after this last lab of taking a wavelength and turning it into frequencies. At least really, really broadly, right? We did that a little bit. If we wanted to do this calculation, we're going to come back to, there are two fundamental equations you need to know. Speed of light is equal to frequency times wavelength, and energy is equal to Planck's constant times frequency. So if we want to answer this question, what's the frequency of orange light? We have a wavelength, and C is a constant. C is on your equation sheet, 2.998 or 3.0 if you only need, let's say that this is 3 sig figs. If you only need 3 sig figs, you can use 3.00 times 10 to the 8. And that's in meters per second. So if we want to get the frequency, and we have the wavelength, we just need to make sure our units are going to cancel out. We're typically given wavelengths for visible light in nanometers. But our C is in meters per second. So the first thing we just have to do is take our nanometers and convert it into meters. And then getting frequency is pretty straightforward. And so 650 nanometers. The nanometers got a multiplier of 10 to the minus 9 on your conversion sheet. How do we write it as a conversion?
1 meter is 1 meter over 10 to the power of 9 nanometers.
We want to be less than 1 meter. We know that nanometers are smaller than a meter. So in other words, it takes a lot of nanometers to equal 1 meter. So exactly right, Jordan. 10 to the 9 nanometers. The way, remember, this positive 9 or negative 9 is this a small unit or a big one? Nanometers are small, so it takes a lot of them to make 1 meter.
Okay.
You get a number, 6.50 times 10 to the minus 7 meters. Now all we have to do is take that and plug in C and plug in wavelength here and solve for frequency. So frequency is equal to C over lambda. And C is 2.998, 10 to the 8 meters per second. wavelength is 6.50 times 10 to the minus 7 meters. We watch our units, we're going to get meters canceling out with meters. We're going to be left in units of 1 over seconds, which seems weird, but that is what the units for frequency are. It's cycles per second. We don't have a unit for cycles. We just say that how many times does this happen per second. So units on a frequency, on any frequency, are always going to be 1 over time. So when we plug this in, we'll get something times 10 to the 14?
Yeah, 4.6.
Give me one more.
6061. Sorry.
And you can write inverse seconds as seconds to the negative 1. You can write it as 1 over seconds, or you can write it as hertz, Hz.
Right.
These all mean the same thing. 1 hertz. Hertz has a Z on the end of it. That's why it sounds like I'm saying 1 and then saying a plural. 1 hertz
What?
is the same as 1 inverse second, 1 over second. Because this is really saying 1 cycle per second. Anything raised to the negative 1 is 1 over that variable, right? X to the negative 1 is equal to 1 over x.
Because the top one was meters over seconds.
Because the top one was meters over seconds, and then we divided by meters, and all we're left with is 1 over seconds.
Okay.
All right, so this gives us our frequency. Our frequency is now, we can write it out, 4.61 times 10 to the 14 hertz.
Just plug it into the.
Then once we want to know the energy, we just plug it into our other equation, right? E equals h times frequency. H is just another constant, like speed of light. Frequency we just solved for. So h is 6.626 times 10 minus 34, and the units are weird. It's joules times seconds.
You just do math in your head?
No, that's a constant. I remember it. Remember it.
Oh, so that's what the.
That's what h is. And then we're going to take that and multiply by 4.61, 10 to the 14, 1 over seconds. So we wind up with units canceling out. Seconds cancels 1 over seconds. We're just left in units of joules. And we should get something times 10 to the minus 20 or so, times 10 to the minus 19.
3.05 by 10 to the minus 19.
That's your energy of a single photon. We want to know the energy of a mole of photons, and this is the energy for 1 photon. What do we have to do?
Times it by.
Yeah. Say 1 photon is 6 times 10 to the 23rd. 6 times 10 to the 23rd photons is 1 mole of photons. So this is joules per photon.
Oh, it's just a conversion.
It's just a conversion.
This is 3.05 times 10 to the negative 19 joules, right?
Correct.
Because that was just the first. Was the energy of 1 photon.
And that's the energy of a single photon.
Okay.
So to then get a mole of photons, we want 6.022 10 to the 23rd photons.
That's just
1
another
mole.
thing that you remember, right?
That's how we got it.
And it's Avogadro's number. It's on the conversion sheet. So speed of light, Planck's constant, Avogadro's number, those are all on your conversion sheet under the common constants section. Right, so you don't have to memorize those either. I just happen to have them memorized because I've done this before. All right. it's about time. Take a break. I'm sure you all agree. But I'm going to leave you with one bad chemistry joke first. This equation, C equals frequency times lambda, gives rise to one of the biggest groan-inducing dad jokes of physics. What's new? C over lambda. No? Remember frequency, the Greek letter nu? What's new? C divided by lambda. But all right. I'm going to blame that on you guys just hadn't taken your break yet. So let's come back a quarter after, and we'll keep going with this.
I have a question.
Yeah.
What's up with the, so you're converting that to moles now?
Correct. Because this last question said, what about 1 mole of photons? This is the energy for 1 photon. Then the energy for a mole of photons, we're going to find that by basically saying, okay, joules per photon, and we're going to cancel out photons to be left in moles.
So it would be like 1 mole photon?
Yeah, so our final number would give us units of joules per mole of photons.
I just got confused because normally it's like photons and then photons would be on the bottom and they would cancel or whatever.
Yes, I very quickly said this is joules for a photon, which means it's 1 photon is that much energy. Therefore, if we want to cancel out photons and be left in moles, we're going to arrange it that way. The only reason to bother doing that is so that you don't divide by Avogadro's number when you're supposed to multiply by it. If you set it up like this, it'll make sure that you multiply by Avogadro's number instead of dividing.
And that's joules per mole.
And then you wind up in units of joules per mole.
I get what you're saying, though, right? Like, that confused me too for a second because I had to go back to the question and be like, what are we trying to find out? Oh, we're trying to find out energy,
Yeah.
not moles.
Thank you for bringing me back to that.
Okay.
I probably should have
That
let you
should
take
be
your
in
break
joules.
before we did this so that you were fresher when you saw this. But we'll do more practice with this. Your one of your quiz questions this week will basically be the same question with a different wavelength. So you'll see it more times.
Well, Sean, were you able to get anybody's conversion rates? Mine's still saying that it's missing.
I have not graded those yet. I think I'm in the middle of grading the math review maybe still.
Cool.
I realized I graded one of them out of order. So normally I'll go chronologically. So if look at your oldest assignments, we'll get ones that get the grades first. The exception being the quizzes. I always try to grade those as fast as I can. And sometimes there's just an assignment that I really don't want to grade for whatever reason. All right, we've got another 30 seconds left, but I'll open with another, since part of it is on this slide. I'll open with another chemistry dad joke. What do you do with a sick chemist? If you can't helium and you can't curium, then you might as well bury him. And I told you it was bad. All right, so this should look familiar, right? These are those tubes we were looking at before. These are slightly different elements. This is probably hydrogen on the, that's probably hydrogen. This might be water or something else. And this is probably CO2 or mercury. So we had some experience with how these work, right? It's just taking a specific element or a compound, pass a whole bunch of voltage through it, which turns it into a plasma basically and allows you to pass a current through it, which makes it light up. The thing is, it doesn't light up uniformly, and different elements will light up differently. We can also do this with a flame test. It's harder to see the colors. You can't actually split it up with a prism the way we did in lab or get numbers because it goes too quickly. This is a classic test called a flame test where you take different metal ions and you dissolve them in something that burns. And then you dip a little loop of wire. They actually make these and sell these specifically for chemistry labs. It's a glass stirring rod that has a piece of wire stuck in the end of it. And that's made for doing flame tests. You get a little bit of drop of that methanol with your ions in it on that, and then you hold it over a Bunsen burner, and different elements will glow different colors as they burn. Same principle as what we did, just using heat from a Bunsen burner instead of using electricity. And the colors are a little bit hard to see on the projector. This one is like your classic flame color. This is sodium. The reason why, if you've ever spilled salted water, if you've ever had salted water boil over on a gas burner, the burner burns like yellow for a couple seconds after that, right? That's actually just heating up the sodium ions enough that they give off this color light. This one is probably strontium. This is potassium. And based on my figure, I think that that's more or less a white flame, maybe with a little bit of a green tint. So it's either magnesium or it could be, it's not copper. Copper's a brighter green. Something else in that same region, it could be nickel. I think nickel will go so whitish with a little bit of a green tint. But it basically works the same exact way. You add enough energy to these systems and they start glowing, and the colors that they produce are based on what element they are. Right? So we made our own versions of these pieces of data. So most of these looked at helium. I think all of you looked at helium. It looked something like this. You might not have been able to see it quite as crisply because they're making these with nicer spectrometers than what we used. And different elements are going to have different wavelengths of light showing up. And all of them, if you compare it to a white light spectrum, that should be a nice even rainbow. The fact that we get these different lines showing up at different energies and nothing in between them tells us something funny is going on with these energy levels. It's telling us we can't have just any energy level we want. Because otherwise, when we heated these things up, we would get a nice even rainbow. So the fact that we don't tells us something's going on. And in fact, you can look at emission versus absorption. And again, a little bit hard to see here, but if you look at the emission spectrum is what we looked at in lab. When you add enough energy to it, it glows and gives off photons of certain wavelengths. If you take that same element and you shine white light on it, you actually see gaps in those same wavelengths. Because those same wavelengths, those are the gaps that correspond with the energy being absorbed by that element. So when you heat it up, it gives off, and call that an emission spectrum. This is an absorption spectrum. This is the colors that are now missing. They essentially get subtracted from the rainbow when you shine white light on certain things. So when we look at the sun's light is an emission spectrum. If we look at how the sun's light bounces off of Mars and we look at what gaps are there when we see the light from Mars, that's an absorption spectrum, but they can still tell us the same thing. They still tell us that Mars is made up of iron oxide, because we can just look and say, oh, well, iron oxide absorbs at these wavelengths. These wavelengths are missing from the sun's spectrum once it bounces off of Mars. All right, and so we can do the same thing with atmospheres, the way we know that certain planets are made of certain elements. It's the same exact thing. We know that Titan, I'm going to mix up the moon. I always mix up the moons. Titan is the one that has liquid methane, I believe, and ethane raining, and it has weather patterns, but instead of water evaporating and coming down as rain, it's methane and ethane. We know that because we can look at the wavelengths of light that are absorbed and say, well, that's definitely ethane and methane because of the wavelengths of light that are being absorbed. So why does it only give us specific wavelengths? And why does it wind up with these whole numbers, these integers, playing a big role? So we used a different version of this equation that was just energy of photon is equal to the nuclear charge times Rydberg constant over an integer squared, right? This is a similar equation rearranged so that we're looking at a difference in energy, and it's basically just done some substitutions and wound up canceling out some variables. But it's the same exact equation, and this is one of the reasons that led why they called it quantum is because the fact that you could only use whole numbers here was weird. Again, it seems like you should be able to have any amount of energy you want, right? You shouldn't be restricted to only these areas. And so this comes together with our understanding of how light's working. And this is what Bohr contributed. Bohr's biggest contribution, aside from being Einstein's comet foil, is the Bohr model. And the Bohr model basically said that, well, we're only seeing certain energies of light because electrons are only allowed to be at certain energy levels. And those energy levels, changing between those energy levels, corresponds with giving off different wavelengths of photons, or photons of different wavelengths. To put it more grammatically correct. So, again, this still seems weird. This still doesn't explain why we can't have an electron of certain energies. But it explains why those integer numbers wind up being so important. Those integer numbers are basically what energy level is the electron in. Higher energy levels moving to lower energy levels are going to give away photons. That energy has to go somewhere. If you have an electron jump from n equals 5 to n equals 2, it's going to create a photon of a certain wavelength that corresponds with this equation. You predict the frequency of light that's produced by looking at the difference in energy from n equals 5 to n equals 2. Again, this still seems like we didn't really explain anything because this is weird, right? It's also worth noting that if we can't have any electrons in between these, the reason why it generates a photon of a very specific wavelength and not a range of wavelengths is because if you can't have any electrons anywhere between 5 and 4, there's sort of this dead zone where the electrons can't exist, which also seems weird, right? But effectively what happens is when an electron goes from one energy level to another, it's not really like you're moving the electron. The electron ceases to exist here and starts existing there at the same time. So it actually goes through a process, mathematical process that we call, in math we call it an annihilation operator, where it's really literally disappears, gone, reappears there. And that difference in energy, though, has to go somewhere because it's not like it can be slowly losing its energy to wind resistance or something like that, like something that's actually changing its orbit around Earth. If it goes from here to there, the energy has to go somewhere. That's where the photon comes from. It creates a photon as a part of the process of disappearing at n equals 5 and reappearing at n equals 2. All of this happening simultaneously. Like I said, quantum doesn't make a lot of sense sometimes. This is what the evidence they were seeing suggests, the evidence that you now have seen as well. You've seen those barcodes in hydrogen's emission spectrum, and the fact that it was all this blank space in between these. Because there is no way that hydrogen can have an electron with this energy. It can have this energy or that energy, nothing in between.
There's such a thing as antiphoton at that?
That's a good question. I don't know the answer to that.
Because looking at antimatter, it's positively charged electrons. If they jump
So the problem is that
orbitals,
photons, while acting like particles, don't have mass. They have an effective mass that we can measure, but the photons themselves, from the photon stream of reference, are massless, which means if you don't have any mass, you can't anti-mass.
okay,
So I don't think so, but I don't know that for sure, so I'll have to look at that.
right on.
All right, so electrons are weird is kind of where we're going with this so far. We'll keep expanding on that. Electrons will continue to be weird. In fact, if you take electrons, so I just got done talking about how photons don't really have mass, but they behave kind of like a particle and kind of like a wave. Turns out electrons, if you shine electrons and do a double slit experiment with electrons, you get a result that looks like you used light. You get these particles that have measurable mass now going through this double slit experiment and causing an interference pattern. But we know that they're particles. We can measure their mass. It's really small, but it's measurable. But they're behaving like waves and interfering with each other. And this is what led to, that's the equation I was looking for. That's de Broglie's equation that says that the wavelength of a particle is equal to a integer number divided by the mass times frequency. So in other words, mass winds up playing a role in the frequency of matter, but matter is not normally thought of as having any frequency.
Can you say that again? Wavelength equals what?
This isn't one we're going to wind up using. This is for historical purposes, so don't worry about that.
Is that the same formula that Einstein used to get E equals mc squared?
Version of it.
Version of it?
De Broglie was before Einstein did E equals mc squared, so he was aware of that, and that factored into how he got to his equations.
Yeah.
All right, so what this winds up actually looking like, we actually have sophisticated enough experiments now, we can track individual electrons hitting a really sensitive screen. That's basically what a CRT is when you fire a high energy electron, if it hits a certain spot, that spot glows for a second. So we can actually track individual electrons, fire individual electrons through one at a time through this double slit experiment. And what we wind up seeing is when we do that and we track the results and we overlay them on top of each other, we get an interference pattern. So when we're tracking individual electrons, we're not even just looking at a whole bunch of electrons at the same time. Individual electrons will interfere with themselves. One electron interferes with itself to cause an interference pattern like this, which is really weird because it's a particle, right? Well, but it's actually also a wave. Mark?
Is that also like TV static?
TV static is background radiation being that your antenna picks up and displays as random noise on your screen. Yeah, absolutely. It's the same thing. It's just instead of taking a radio signal and turning it into a picture, that coherent picture that means something to us, we're just getting random background radiation from the sun or whatever else is happening that just turns into white noise on your screen. All right, so how does this work? How the heck do we get an interference pattern for individual electrons interfering with themselves? This is a two-slit experiment, right? So how are we getting an interference pattern when an electron has to pick one of these two slots to go through, right? Well, if it has to pick one of these two slots, how can it interfere with itself? Because the interference pattern only happened when you had two slits, and then you had the wave from this slit interfering with the wave from that slit. So what this actually showed is that when you're measuring over here, a single electron goes through both slits. One particle behaves like a wave to the point where it actually goes through both of these slits simultaneously. Which just gets into the whole Schrodinger's cat thing. We'll get to Schrodinger in a minute. It turns out if you measure which slit it goes through, the interference pattern disappears. If you measure which of these slits has an electron pass through it, it behaves as a particle, not a wave anymore.
I'm sorry, what?
So it turns out observation changes the system. By observing which slit it goes through, it forces it to act like a particle instead of a wave. So what happens then, if you're monitoring which slit it goes through and monitoring over here, the interference pattern goes away and you just get a bar on the left and a bar on the right, like it behaves like you're throwing baseballs through a door. But if you don't monitor which one it goes through both, and you get an interference pattern.
How did you monitor which one it goes through to contact and happen?
So you could do something like measure if there's any charge that passes through one side versus the other. So the electrons are charged, right? So you can measure the charge. Or you can actually do something like look and see if there's any light that comes from one. You can be bouncing light through this, and if there's any light that hits an electron, it's bounced off a different way, you'll see a tiny signal that corresponds with the photon bouncing off of the electron. So they have ways of measuring which slit it goes through. And the act of measuring,
turn different.
you change the results just by watching which slit it goes through.
How did they watch that first one?
So this one,
Yeah.
we've been not observing which slit it goes through. If you don't observe which slit it goes through both, and it acts like a wave, and you get an interference pattern.
Couldn't you just measure them one at a time and then just combine the measurements at the end though?
That's what they do here.
Why is it changed by observation?
So there are a couple things. So that's actually what Heisenberg uncertainty principle is. Heisenberg uncertainty principle, at its root, says that your uncertainty, I'm going to forget what the constant is, that there's some constant is the product of the uncertainty in the position of a molecule times the uncertainty in the momentum of that molecule. I want to say it's that the constant is Planck's constant over 2 pi or something like that. Planck's constant's involved. But basically, these two sigmas represent the uncertainty in where something is. By measuring which slit it goes through, we're measuring this really accurately. It's either here or it's there, which means your uncertainty in its momentum goes up.
And then wouldn't you just do the exact same problem again, but making the left one the other side?
Except if you measure with the momentum, you don't know where the particle is. You can only know one of these two things with certainty. If you know the position, you can't know momentum. If you know momentum, you can't know position. And for most of these things, there's a mass term involved here too. So for most, this is true for everything. But for most things, the mass is so big that the uncertainty is tiny. But when you get to small enough masses, the uncertainty winds up being measurable. It winds up affecting things, and you get weird stuff like this happening. And the way we kind of explain it is that an individual electron doesn't behave just as a particle, which means it doesn't follow a classical particle trajectory. So when we think about throwing a ball, we can predict where that ball is going to go. It's going to be roughly parabola shaped. You know, we could get more complicated and take wind resistance into it if we wanted to. But a ball is big enough that these two uncertainties wind up being really, really small. But when you get to something that's small enough, you actually get something where you can't know exactly where it is and where it's going at the same time. And so what you really get is what's called a probability distribution that shows you where the ball probably is. The ball is probably in this area. But we can't know exactly where it is, because if we measured exactly where it is, we'd measure it in a way that would change it. If we look at an electron, if we measure where an electron is, like Grace was asking about, if we measure where the electron is by bouncing photons off of it, we change the electron's energy now by bouncing a photon off of it. And now that means that electron's going to bounce off in a different direction with a different energy than it had before. Or if we measure where an electron's momentum or velocity, we can't know where it is anymore. We know what speed it's going, but we don't know where it is anymore. Because the product of these two uncertainties has to be greater than or equal to a constant. So, go ahead.
Is there a way that, like, if we could discover, like, a different way to measure it, it could maybe work? Where you know both?
Everything we know at this point says no. So I'm not saying that it couldn't be done, but as I understand it, this is a fundamental rule of how the universe works. You can't know a particle's position and momentum simultaneously, because the universe has inherent uncertainty to it. And you can't get these uncertainties to be zero. And the more accurately you know one, the greater your uncertainty on the other one. These are inversely related, right? So if you have a general idea of where it is, you can also have a general idea of what its momentum is. But the second you start measuring exactly where it is, this uncertainty goes up. And so we treat it more, it's a little bit like looking at the average of a whole bunch of measurements at the same time. If we had a pitcher throw the same pitch 100 times and track the trajectory of all 100 of those and overlaid them onto each other and made sort of a heat map, we would get something that was kind of like this probability distribution. So we could say that for the next pitch, there's a highest probability that it's going to be right along here. There's also some other probability that deviates a little bit from that. So, and this is kind of how we treat electrons. We basically say, okay, well, we can't know exactly where they are. They're so small that measuring changes the entire system. So we're going to come up with some mathematical functions that describe where they probably are with 95% certainty. We'd say 95% certainty maybe that the next pitch is going to be in the same area. We do the same thing with orbitals and electrons. And so I just used a term I should probably define. An orbital is kind of like an energy level. It's just a more specific term. An orbital is the mathematical function that describes where you're likely to find an electron and also has its energy sort of embedded in the shape of it. So an orbital has its own energy, and electrons that are in that orbital, you can tell more or less where they are and what their energy is. Jennifer?
But that has to be in relation to the nucleus though, right? I mean, we're not
It
taking
does.
them off of the element.
It does. So we're gonna look at a vibrating guitar string as a way of understanding this. So, and we'll try and plug it in and demonstrate. I mentioned this to yesterday's class. I used the term harmonics and got some blank stares. So I'll demonstrate how this works a little bit. My daughter was the last one playing with this, so let's make sure it's not too loud. So if we have a guitar string vibrating, we can think of this as being like an electron around a nucleus. There is some area where the guitar string is. It's either between here and there. We don't know exactly where it is at any given point, but it's somewhere in between those two. So you can think of this as a probability distribution. And that's like if we just pluck an open string let it vibrate from here to here. So we can also, though, if we wanted to move it to a higher energy level, a higher frequency, we can shorten the wavelength while still keeping it to the same overall wavelength. The whole string is still vibrating. I still picked the same string, so open. If I let it vibrate, except for right in the middle, I can shorten the wave, which changes the frequency, right? Because wavelength and frequency are inversely related. You can add another wave. You don't even have to keep your finger on it. It's not like shortening the entire wave by actually pressing down on the fret. So that's pressing down on a fret. I'm not pressing on a fret. I'm basically just not letting the string vibrate at the exact point in the middle, or a third of the way. And then I can take my hand off it. All I'm doing is I'm starting it by not letting it vibrate there. I'm putting it into a different function by not allowing it to vibrate in a certain spot. And there is not really any note in between these. You can imagine there's one more. It's a little bit higher. That'd be if I put my finger exactly a quarter of the way. And so the different energy levels that the electrons are allowed to be in correspond to the way that you allow these waves to connect. Right? You can have open string. You can have a wavelength that's exactly half of that. You can have a wavelength that's a third of the open string. If I tried to do the same thing, but putting my finger randomly, nothing happens. But the second I put it in the right value, if I make the wavelength right, I can get a vibration to happen. So this is basically what's happening at the quantum level. Just why we can't have electrons with just any energy. They have to have energies that correspond with putting the nodes in the right spot. The thing is that we're not dealing with these two-dimensional straight lines for these functions. As Jennifer mentioned, this has to be around a nucleus. So what we actually get is something that looks kind of like a wave, but in spherical coordinates. So it's a wave, still has up and down, but in a circle instead of being connected at two ends. Picture taking those two ends and connecting them together. And then going to higher energy levels corresponds with adding additional nodes, adding extra spots where there's no vibration. The thing is, even this is an approximation because this is still really only two-dimensional, right? It's a circle, but it's still two-dimensional. So this is really happening in 3D and spherical coordinates, and it looks like a sine wave in 3 dimensions that actually has a 4th dimension that's the probability. So it's a little bit like having a bell curve embedded in a 3-dimensional function. So mathematically, it gets very complicated very fast. If you think of up and down as being the probability of finding an electron at that spot, and where it hits 0, there's no chance of finding an electron there. You can see how this is kind of like a bell curve, where you wind up with, okay, well, there's probability I find it here, or there, or there, or there, but not right here. That's just like with the guitar string vibrating, having that spot where no vibration occurred. All right, so when we do this in 3 dimensions, they look even trickier. The simplest ones still look like a sphere, basically. But then you wind up with these other things that are, these other functions that are more or less a sine wave in spherical coordinates in 3 dimensions. So you wind up with something that looks kind of like a figure 8, where this is the origin, and these things are kind of shaped like balloons. And these functions tell us physically around the nucleus. The nucleus is going to be right here. Near the nucleus, there's going to be these functions that show us where we're likely to find an electron. We don't know exactly where it is. We know that if there's an electron with this specific energy, it's going to be in this. It's not an area anymore, it's a volume if we're in 3 dimensions. This volume probably contains the electron somewhere in there. Just like those other functions probably contained where the guitar string was vibrating at any given time. Right, so without measuring exactly where the electron is, we can have an idea of where it is, and we know what the energy is associated with these functions.
Is this just one electron that could be in either one of those?
Correct. This is one orbital that has this whole figure 8 shape, and so the electron could be here or there. Right, and so when we start looking at this, is all kind of connect back to the periodic table and the way the periodic table is shaped. Because remember, I told you that everything that changes, every chemical reaction, is the result of electrons moving in different energy levels. So the periodic table has the shape that it does because each orbital and each orbital type, there are different types of orbitals we'll go over in a minute, can only hold so many electrons before it's filled and you have to start putting them somewhere else. Right, so the first energy level can only hold 2 electrons. The first energy level, n equals 1, only has one type of orbital. It's what's called an s orbital. And that s orbital can only hold 2 electrons. So once you've added 2 electrons to an atom, that n equals 1 energy level is full. And if we want to add any more electrons, we have to go to another energy level, n equals 2.
Sorry, how many electrons did you say?
So first energy level can only hold 2 electrons, which is why the first row of the periodic table only has 2 elements in it. The periodic table is shaped the way it is because it tells us when we fill up an orbital or when we fill up an energy level. The first row of the periodic table only has 2 elements in it because n equals 1 can only hold 2 electrons. The second row of the periodic table can hold 8 electrons. 2 of them in what are called an s orbital, and then you add another type of orbital called a p orbital. And if you look at the periodic table I've given you guys, they're actually labeled s block, d block, p block. That's actually going to be telling you the types of orbitals that you're looking at, where we're putting our new electrons as we go up. So these animations do not translate well between versions of Excel.
How many electrons can be held in the third orbital?
So I'm glad you asked that. So let's finish talking about 2 first. So the first thing that you get is you get n equals 1 for the first energy level. You only get one type of orbital called an s orbital. We call it the 1s orbital, the s orbital that goes with the first energy level. Once that's filled, we have to go up to n equals 2, which has an s orbital, so we call it the 2s now. But then we can also have a p orbital. In the p orbital, so this is the 2p orbital, a p orbital has 3 different of these figure 8 shapes. One figure 8 that's sort of aligned around each of the 3 dimensions, x, y, and z. So if we call this z, there's another figure 8 that goes, let's see, x is going to be back this way, so there's another figure 8 that goes along the x-axis, and then another figure 8 that goes along the y-axis. So we have basically 3 ways we can orient these figure 8 shapes along each of the 3 dimensions, which is why there are 3 ways we can put electrons into this type of orbital. The s orbitals just look like spheres. They just look like balls. There's only one way we can do that, and each of them can only hold 2 electrons. So we represent these electrons as being an arrow up and an arrow down, because there's another property called spin that says you're allowed to put 2 electrons into each of these lines. These lines represent the different energy levels, the different orbitals. But the p orbitals, there's 3 p orbitals, 3 pieces to a p orbital, and each of them can hold 2 electrons. So this s block is 2 elements across, because that corresponds with how many orbitals or how many electrons you can put into an s orbital before it's filled. You fill an s orbital once it has 2 electrons in it. And then you have to go to another type of orbital or to a higher energy level. So when you look at the periodic table, it goes 1, 2, and we filled up the first energy level. 3, 4, both go into this 2s orbital. If we want to add any more electrons than that, we have to jump over to the p block, which means we're putting electrons into a p orbital now. And a p orbital can hold a total of 6 electrons before it's filled. So the second row of the periodic table holds 8 electrons total, 2 in an s orbital and 6 in a p orbital.
Same with the third row, right?
The thing with the third row, and this will be the last thing before we're done for the day, is every time you go up an energy level, you add a new type of orbital you can make. So you actually get a 3d orbital, but it's so high in energy that you don't start filling it up till after you go to the 4s. The rule for these, though, is always going to be, they're always going to go in the same order, and you're just going to add electrons until you run out. So if you have a total of 10 electrons, you start down here, you start writing in arrows until you get to a total of 10 arrows. And that tells you how many electrons and in what energy level are they going to be sitting in. And I know normally I would immediately go into some practice with this, but we're out of time for today. So what we'll do instead is we'll cover that all again, because you're going to need to hear it again on Thursday, and then we'll practice with what does this matter and how do I use it. Okay? All right. Have a good day, everyone.
Let's do.
Everything's due Thursday. I just made the due date for both the lab and the iSave from last week is both due Thursday since there was some confusion.
Okay, thank you.
No problem.
Which lab is due Thursday? The one we did yesterday?
Chromatography.
Yeah, chromatography from last week. We may have already turned it in.
All right, I finally drink my cream soda.
Thanks, Sean.